Greetings. Welcome to lesson 25B. Like lesson 25, this lesson is also on studying a power system that contains a delta load. I have changed the line impedance of example in lesson 25 to a smaller value and have specified the load voltage instead of the source voltage as it was done in lesson 25. Just as in lesson 25, I will be calculating for this system the line and phase voltages, real and reactive load power consumption, real and reactive line power losses, power factor efficiency, and voltage regulation. In lesson 26, I'll use the example of this lesson to show the application of the capacitors in raising load power factor. Since there's not enough space on the slides for statement of the problem and the lines of solution that will follow, I'll state the questions of this example verbally. We're looking at a balanced system with delta connected per phase load impedances of 90 plus J75 ohms and per phase line impedances of 2 plus J6 ohms. Line-to-line voltage of the load is given as 4800 volts. I have assigned this voltage with zero phase angle to VAB of the load as our reference voltage. Here it is, VAB equals 4800 with 0 degrees phase angle. To reduce clutter on the diagram, I have marked only one load impedance, and the other two are going to be the same, and also have marked the impedance of one of the three lines, and the impedance of the other two lines would be identical. We're asked to find the line currents IA, IB, and IC, load phase currents IAB in this direction, IBC, and ICA, system voltage regulation, real and reactive power delivered to the three-phase load, real and reactive power lost in the three lines, real and reactive power generated by the source, real power efficiency of the system, and power factor of the load and of the combined load and lines. One approach for analyzing systems of this sort is to convert the delta load to its equivalent Y-connected load, use the equivalent line to neutral circuit to find the line currents, find the required quantities that are asked for, and go back to the original delta load and calculate the load phase currents, as well as any other quantities that may still be outstanding. I had discussed the general formulas for converting between delta and Y-connected impedances in lesson 14, and you can refer to that lesson if you would like to review the general case. However, for balanced loads, the conversion process is quite simple. You just need to divide the per phase load of a delta connected set of impedances by 3 to get to the Y connected impedances that are equal. So here it is, ZY equals Z delta over 3. And so each leg of the Y for this example will have an impedance of 30 plus J25. The next slide has the Y-connected equivalent load. And here is the converted load. The neutral conductor that's inserted here is only to help us with our analysis of the system and is inconsequential to the overall function of the system as it does not carry any current. From the line-to-line voltage of the load VAB, we can find this line-to-neutral voltage VAN between these 2 points, and VAN is found as VAB over square root of 3 with negative 30 degrees, and that's because we know that the line-to-line voltage VAB equals, in a positive sequence system, would be square root of 3 times VAN, and it will have 30 degrees extra in its phase angle, so plus 30 degrees. So we can calculate VAN in terms of VAB by dividing over square root of 3 and assigning a negative 30 degrees for its phase angle. Substituting for VAB from here in this equation, we have VAN comes out to 2,771 volts with negative 30 degrees angle. That's the voltage between phase and neutral of the load. Having the voltage across the load between points A and N, as found here, we can find the current through the phase as VAN over this impedance here. And of course, the same current that goes through the phase is the current that is coming from the generator over the lines. So we're actually finding IA, and by dividing the voltage over the impedance of the load, and IA comes to 70.97 amperes with negative 69.88 degrees of phase angle. Subtracting 120 degrees from this phase angle will give us IB, calculated, shown here. And subtracting another 120 degrees from this one will give us IC, that's given here. Next, I'll calculate line to neutral voltage VAN of the generator. And we'll do that by adding the voltage drop on the line plus the VAN, the line to neutral voltage at the load. And here's that equation. VAN equals IA times Z, 2 plus J6, because we know the impedance here is also 2 plus J6. So this voltage drop, this term, plus the voltage drop across the phase of the load, which is the VAN here that was found in this line here. Putting these values in, VAN for the generator, line to neutral at the generator, comes to, well, it's calculated as this voltage plus this current here times this impedance. And that comes to 3,162 volts with negative 25.72 degrees phase angle. Generator line to line voltage is found by multiplying this by square root of 3 and adding 30 degrees to its phase angle. And that's done here. VAB from this point to this point on the generator side comes to 5,476 volts with 4.28 degrees of phase angle. I'll now summarize some of the results that have been calculated so far and are going to be needed moving forward. And those are here. Now let's move on to calculation of voltage regulation. Voltage regulation is calculated as difference between no load voltage and full load voltage, both calculated at the load location, divided by the full load voltage and converted to a percentage. The full load line to line voltage at load was given already as 4,800 volts. And the no load voltage would be the same as the generator voltage VAB that was just calculated here. The reason that no load voltage at load is equal to VAB of the generator is that once you remove the load, if the load doesn't exist anymore, the currents will drop to 0, and therefore there's no voltage drop across the lines. and so the voltage of the generator will directly show up at the load location. Here is the equation form of the voltage regulation. Sometimes this is designated as VR in abbreviation. V no load minus V full load over V full load. And we have all the values we need. V no load is the voltage of the generator, plus or minus VAN given here. VAN given, oh, VAB, excuse me, given here. Minus the line-to-line voltage at the load, at full load, which is 4800 over 4800. We could have used line to neutral voltages all the way through and would have gotten the same answer, but I've used the line to line voltages, and the answer is around 14, a little bit over 14% is our voltage regulation. If the line to line voltages of the load were required, they can easily be found by rotating the VAB by 120 degrees in the clockwise direction, because we're working with positive sequence system. So VBC would be 4800 with negative 120, and VCA would be 4800 with positive 120 degrees. I'll next find the real and reactive powers of load and line and the generator. I'll first find the single phase quantities of power, and then we'll triple the answers later to get the three-phase powers. Single phase complex load power is found as VAN times conjugate of the current, IA. Putting in the values of V and IA, we get this value, 2771 with negative 30 degrees, times the conjugate of IA. Well, the conjugate means it will have the same magnitude, but its phase angle sign will be reversed. So we go from negative to positive here. And the product in Cartesian form will give us the complex power of the load for a single phase. The real part of this complex value, the real part of it will give us the real or active power of the single phase of the load, and the imaginary part will give us the reactive power. And I wrote those explicitly out here. Load power for a single phase is, the real part is 151.08 kilowatts, and the reactive part of the power is 125.92 kilobars. The apparent power is found as square root of the sum of the squares of the real and reactive powers, shown here. It comes to this number. In volt amperes, I converted that into kilovolts amperes as 196.68 kVA. Load power factor can be found as cosine of the difference of phase angles between VAN and IA, and those values are here. You can subtract one from the other and you'll end up with an angle of 39.81 degrees. And taking cosine of this will give you the power factor. Or it can be found by dividing the real power over the apparent power, as I have done on the next slide. You can see that operation here. Load power factor equals load real power, 151.08 kilowatts, over load apparent power, all for single phase, which is, well, in kVA is this number, 196.68. And the power factor comes to 0.768, and I marked it lagging because the current lags the voltage. You can see that the angle of the current is more negative than the angle of the voltage. On the next slide, I have summarized the load powers and the power factor that was just found. And here they are. I'll next calculate the single line power loss, the power loss in the lines, but just for one of the lines, by multiplying the square of current times the Z line shown in this equation here. S of line for single phase is I squared, magnitude of I squared, times Z of the line. And substituting for the values, we'll have 70.97 squared from here times Z of the line. And that comes to this complex number in Cartesian form. So the line real and reactive powers are extracted from this complex number. Real power of the line, real power loss on the line, I should say, is 10.073 kilowatts, and reactive power loss of the line per line is 30.22 kilowatts. I can multiply the line to neutral generator voltage VAN by conjugate of the line current to find the single phase generator complex power. We have VAN calculated earlier here, right here, and we have IA, of course. We can multiply VAN times IA conjugate to find the single phase power of the generator. However, since we already have the load power and the line power loss, we can instead add these together to find the generator power. I have found the power by this second way shown on this slide. So the source real power is the real power loss of the line plus the real power of the load, and generator reactive power is the reactive power loss of the line plus the reactive power of the load, and those are the values for the source, again for a single phase. Summarizing the results to this point, here they are. System power factor, which is the power factor seen by the generator, as usual, can be found in a couple of different ways. I plan on finding it by dividing the real power over the apparent power. First, let's find the apparent power of the generator. It is done in the usual way of squaring these two quantities, adding them together and taking the square root of the sum, and that comes to 224.39 kVA. And the power factor for the system, looking from the generator into the system, is calculated as the source active power over the apparent power, and that comes to 0.718 lagging. Note that the system power factor that was just found is lower than the load power factor. The reason is that the highly inductive line impedance is added to the load, which itself happens to be an inductive load, and so it becomes even more inductive, which lowers the power factor further. I'll summarize the powers on the next slide. Here they are. Single powers of the line and the load and the source. Next, we'll multiply each single phase power by 3 to find the three phase powers. And they're shown here. Put these back on the left, all of the three phase powers. Efficiency is found as the power out of the system as a useful power that goes to our load, divided by the power that was put into the system. In other words, the power of the generator that was fed into the system, some of which has been lost in the line. I have the efficiency calculated on the next page. Equals the load power over the source power times 100 comes to 93.7%. I've used the three-phase powers, but we could have also used as well the single-phase powers because they're proportional, so the answer would be the same. Let's now go back to the original system with the delta load and find the phase currents of that load. We can find the phase currents by dividing the line-to-line voltages that were found by each phase impedance. Or we can use the line current instead. I use the second method starting on the next slide. We have IA, and we know that IA is in positive sequence systems is calculated as the square root of 3 times phase current IAB with negative 30-degree angle. And from that we can find IAB, which is what we're looking for, as IA over square root of 3 with positive 30 degrees angle. And here is that equation, IAB. Substituting for IA, we can find the IAB. So IA coming from here over square root of 3 and add 30 degrees to what you have here. And you get 40.97 amps with negative 39.81 degrees of phase angle. That's this current going through this phase. The other two phase currents are simply found by clockwise rotation of IAB as 120 degrees once and then yet again next for ICA. So subtract 120 from this phase angle and you get IBC phase angle, and add 120 to this phase angle to get the phase angle for ICA. Just as a check on the value of IAB that we found, I'm going to divide the voltage across this impedance by the impedance, and to make sure that we get the same answer as a check. And here it is. So I have 4800 with 0 over 90 plus J75. And that comes to exactly the same answer that we found here. 40.97 amps with negative 39.81 degrees. We have reached the end of lesson 25B. In lesson 26, I'll use the circuit we have worked with here and show how to add capacitors in parallel to the load to improve the power factor of that load. My name is Fouad Albandi. I'm a PE in Electrical Power Engineering. You'll find my name, web address, and email address on this page. The web address is own-your-destiny.mylearnworlds.com, and the email address own-destiny@yahoo.com. I invite you to visit my website when you have the time. You'll find comprehensive modules on different topics of power systems engineering on that website. Thanks for watching this video, and if you enjoyed my presentations, please click on the subscribe button and the notification bell. I hope to see you soon in another one of my presentations.